జాయిన్ అయి ఉంటారు చూడండి.
ఎల్లో కలర్ బుక్
హలో,
A very good morning, dear participants. Welcome to the last day of the one-week international online FDP on trends and challenges in development of electric vehicles and hybrid electric vehicles, Series 1. I hope you have learned much from the past few days. This morning we have with us Dr. Krishna Kumar Gupta sir from Thapar Institute of Engineering and Technology, Patiala, and who will be sharing on the topic Advanced Power Converters for Electric Vehicle Charging. Before I give this time to sir, I invite our convener for the event, Dr. Sridhar sir, to introduce the speaker for this morning. Over to you, sir.
good morning to all the participants of this fifth day session. Welcome to Dr. Krishna Kumar Gupta sir. Sir is the speaker for today's session. Very few eminent persons are doing research in the area of electric vehicles across the globe. One of the person is Dr. Krishna Kumar Gupta sir. Thank you very much, Krishna Kumar Gupta sir, to be with us for this section. I want to speak a few words about Dr. Krishna Kumar Gupta sir. Sir did his B.Tech in Electrical Engineering, M.Tech in Power Systems, and PhD in Electrical Engineering, all from NIT Bhopal, Congratulations, sir, for getting this type of opportunity. Very few persons get this opportunity to complete the education from the same institute, the two eminent institute, Maulana Azad National Institute of Technology, Bhopal. Sir, interest areas are topologies and control schemes of multi-level inverters, power converters for renewable energy applications, fault tolerance power converters. He has more than 60 publications in Science Citation Index, and Sir also published some books. One of them is Multi-Level Inverters, Conventional and Emerging Topologies and Their Control, published by Academic Press Elsevier. And Modeling and Control of Power Electronics Converter System for Power Quality Improvements. This is also by Academic Press Elsevier. And Sir has patent grant also, cascaded multi-level inverter. And Sir has many achievements, awards, and recognitions. He received Young Scientist Award conferred by Madhya Pradesh Council of Science and Technology, Government of Madhya Pradesh, during 30th Madhya Pradesh Young Scientist Congress held at Vignan Bhavan, Bhopal, during March 2018. Sir is with an eminent institute which was established in 1956. And Sir is going to deliver his talk on advanced power converters for electric vehicle charging. Thank you very much, Krishna Kumar sir, for accepting our invitation to address on this occasion of program on electric vehicles and hybrid electric vehicles. Please, sir, please start your section. Dear participants, please wait. Our speaker will join soon within a couple of minutes. Please be online. Dear dignitaries, speaker sir has some connectivity problem. Please wait for a couple of minutes. He will join soon.
Sir, is it audible now?
Yes, sir. It's audible, sir.
Okay, I'm so sorry for
Audible,
taking so
sir.
much
No
of your
issue,
time.
sir. Please, sir. Please, sir.
Yeah, so I'll start right away.
Yes, sir.
I'm doing it.
Please check the screen sharing, sir.
Yeah, sure. Yeah, is my screen
Yes, sir.
visible?
Yes, sir.
Okay.
Screen is visible, sir.
Okay, sir. First of all, thank you very much, Professor Sridhar, for giving me this opportunity to speak on this faculty development program. And I apologize to all the participants for taking so much of time in doing the setup. Actually, I tried with the three different laptops, and I tried with an earphone and microphone also, but it was not working somehow. So this is another machine that I'm using. So before we start, like I would like to uh, quote a very famous uh, these famous words from Victor Hugo, that no force on earth can stop an idea whose time has come. I sincerely feel that electric vehicle is such a technology which is going to dominate this world for a long time to come. And actually, what like before accepting this invitation first to speak on this FDP, what was very intriguing to me is that Professor Sridhar, he is from mechanical engineering department, and he was taking so much interest for this FDP, because primarily like people have a conception that electric vehicular technology is uh, it is like a main domain of electrical engineering, which is not true actually. Apart from the vehicle itself, like the structure and all, today I'm going to discuss many things which form the core part of mechanical engineering. So I believe that in this congregation we have many people who are from mechanical engineering background, and some of you like are from electrical engineering also. So I'll try to keep this presentation in a manner that uh, you can appreciate the application of mechanical engineering in the development of the charging systems for electric vehicles. So while doing so, like it may also happen that I go into very basics of electrical engineering, and the people from electrical engineering, they may find it to be of very fundamental nature, but those things are important actually for design and development of a charging system. Mechanical engineering has a very core role to play in these developments, not just from the structural point of view, but from other aspects also, which I'll be talking about in a while. So today's discussion, like it will be mainly about the power converters, but before that, we will take an overview. Like the title that we finalized for this talk is about advanced power converters. So I'll discuss in detail why do we need to have advanced converters, because the power converters and power electronics technology is now at least 50 years old. So we have very established kinds of converters which are being used in a number of applications. So what is the need for any further advancement in the converters themselves for electric vehicle technology? So I'll be covering many examples, many practical examples of the commercialized vehicles to emphasize on this point on why further advancement. So while doing so, like you may appreciate some of the points which you may like to take up your own research also. So after that, like we will be discussing about classification of converters, and then I'll talk about a very latest development which has taken place in the evolution of converters for electric vehicles, and I'll explain it with the help of few experimental results and the applications where this kind of research can be used in electric vehicles. And thereafter, we'll be concluding this talk. So during the talk, please feel free to ask any questions that you may have, and I'll be very happy to discuss those things. So this is a typical powertrain which is used in an electric vehicle. This is, of course, from the perspective of an electrical engineer. The mechanical engineers which are present, they can appreciate the simplicity of this kind of architecture, because when a vehicle is based on internal combustion engine, then the architecture, the technology itself actually is very much complicated, the IC engine technology. And this is the main reason why many manufacturers, they cannot build an IC engine based vehicle, whereas many of them can easily make an electric vehicle. You see, especially in India, like the penetration of electric vehicle has started from what we call as e-rickshaws. So in your own city, you may find a number of vendors which are assembling e-rickshaws and they are selling it, right? But not many manufacturers can actually build a three-wheeler which uses an IC engine. So basically what happens here is that you have a battery bank which acts as a source of power. You have an electric motor which provides mechanical power, and in between there is a converter which takes care of the conversion process, and that's it. That's how simple an electric vehicle powertrain is. So this is a typical powertrain that I'm showing here. So in the course of our discussion, we will be focusing on this part, the battery pack. I'll take some practical examples to demonstrate how the manufacturers are deciding about the battery packs. The motor itself, there is a huge range of motors which can be employed for this traction system. And today's talk, like, we will be discussing about the charging system itself, which is actually the main reason why people are not so much taking this idea of electric vehicle, because everyone is worried about refueling, right? For a gasoline based car, you have a very easy, very established refueling system where you stop at a petrol pump and it hardly takes 5 to 10 minutes to get fully refueled. So charging system is an important bottleneck which has to be addressed. But the thing is, like, before investing into charging stations, many business people, they are more concerned about the penetration of the electric vehicles. So this is a question of like, what comes first, the chicken or the egg? Like, many people will purchase electric vehicles when they find that numerous charging stations are existing. But the development of charging stations is going to take place if the investors, they find that a promising number of electric vehicles is there. So this is a big challenge for the government, and you may find many schemes which are coming up to increase the penetration of electric vehicles. From the perspective of the grid, an electrical engineer, the power system engineer, this is how the whole infrastructure can be overviewed, right? So again, like, you will be using electricity, so the power generation becomes very important, and in that, the power which is generated by renewable energy sources, maybe photovoltaic sources or wind energy, it is going to form the backbone of this system. Because when we talk about the advantages of electric vehicle, we are always speaking about the reduction in the carbon footprint. So if we are going to burn the fossil fuels to get this electricity, then there is no point of using electric vehicles for the purpose of reducing pollution, right? Because it's not going to reduce it. Only if we have more reliance on renewable energy sources, then only like a widespread use of electric vehicle makes more sense. Anyway, that is a secondary issue, not the core part of today's discussion. So what you might be aware of is the home charging, which is used for electric vehicles. So basically, this home charging has a limitation of power. You are using single phase power, and typically this power cannot be more than 10 kilowatts or so. So which means that the transfer of power to the batteries is less, and hence the charging time is more. More commercialized systems, they use three-phase power, and therefore you can uh, you can realize fast charging stations using three-phase sources. So here, basically, what is happening is the amount of power which you are transferring is more, and hence the battery gets charged fast. So we will here they talk about AC fast charging as well as DC fast charging. So what happens in DC fast charging is that you are directly accessing the batteries of the car. You're bypassing what we call as the onboard charger, right? So in DC fast charging, you are directly accessing this battery pack and you are charging it. Whereas in AC fast charging, you are taking help of the onboard charger, which converts the AC to DC and which in turn charges the battery. So we will have look on both these types of charges. A brief introduction about the types of chargers before we go into some of the practical aspects. So like I said, the broad classification is in terms of where the charger is placed. So if the charger is placed on the vehicle itself, then it is known as an onboard charger. Whereas if it is not the integral part of the vehicle itself, then it is known as an off-board charger, and in our language we call it as a charging station. So onboard chargers can again be of two types. They can be either of dedicated type, where they are basically converting the AC into DC, or they can be integrated into the electric motor itself. I'll give you some examples of the cars which use these integrated chargers. Now, as far as off-board charging is concerned, I talked about AC chargers which make use of the onboard charger, and DC chargers which basically directly access the batteries, right? There are some other techniques like battery swapping. Battery swapping can be very much successful, especially for two-wheelers and for three-wheelers for loading applications. Wireless charging and dynamic charging, they are also coming up very fast, but this technology is going to be, as of now, it is going to be very expensive as compared to the wired charging. Similarly, the charging standards, they are not uniform throughout the world. Number of charging standards are there which are still actually evolving, both for DC charging and AC charging. But the pioneers in this field, like you're all aware, like Tesla has been the pioneer in this field of both AC charging and DC charging. So for the uninitiated, and for the people who are not into this kind of research, like what is the general architecture of EV charging? So basically what is happening is that this battery is what is powering your car, right? So it has to be charged, and this battery is a DC source of power. So for charging, actually it needs uh, electric power in DC form. So when I talk about DC, which stands for direct current, it simply means that if you have this device with terminals A and B, DC means that the direction of the current never changes, right? This is a very layman kind of definition for DC. If the direction of current does not change, then we call that current as DC. But our power system if you see, it is the power system itself is of AC nature. So alternating current, we know that this type of current is such that it periodically changes its direction, which means that for some amount of time it flows from A to B, and for some equal amount of time it flows from B to A, and this process keeps happening. So our grid, whole of the power system, is basically working on AC. So this is what actually generates the need of uh, EV charger, that the source that you're having either at your homes or at commercial locations, the source is basically an AC source, whereas the battery, which will now act as a load, it requires DC. So the common sense tells us that you need to convert the AC from the grid to DC, which is to be fed to the battery. So typically, the EV charging system has two stages. This is the stage one, where you are rectifying this AC to DC. And this is the second stage, where you are using a DC to DC conversion for controlling the current which is fed into the battery. So these are the typical two stages of an EV charging system. We'll take more detailed look on what kind of uh, topologies are required at stage one, but we'll go into it at a later stage. But this is the basic requirement. You have to convert AC into DC, and you have to fine tune that DC to a level of the battery voltage itself, so that you can efficiently charge it, right? So this is a typical system for EV charging. Now I'm going to take some examples of the commercially available vehicles, and we'll see like what kinds of systems that they are using. I don't want you to like focus too much into the circuit itself, right? I just want to give you an idea of the wide range of actually the circuits which various manufacturers are using, and the challenges that they are facing, and the challenges that we are facing as researchers in this field. So one of the like pioneering vehicle in electric vehicle technology has been a car known as Volt, right? So it is manufactured by Chevrolet. So this is the onboard charging system for this Volt, this vehicle Volt. And here you see that this is the battery pack, and this is the on your left is the grid. So this whole system is basically for conversion of AC to DC. So this again, this here you can see this has numerous stages. This is a stage, simple diode rectifier stage. This is a boosting stage, and this is a stage which is actually controlling the current which is being fed to the batteries. One important thing that we should all notice here is that the use of a transformer, which is basically for providing an electrical isolation between the battery and the grid. This isolation is extremely important from the safety point of view. We don't want a conductive connection between the grid and the battery for the safety of the people inside the vehicle. So this isolation is now a mandatory requirement from various like agencies, right? For you to manufacture an electric vehicle charger, you must incorporate some kind of isolation for the safety of the people inside the vehicle. This is a three-phase charger. You can see the grid here is a three-phase grid. This is a charger which is being used by the Tesla vehicles. Again, if you see here, the number of stages, it looks less. Again, there is an isolation, and the circuit looks a bit complicated, but we'll get into it at later stage. This is what vehicles in Hyundai they are using. This is again an onboard charger, single phase charger, but this charger is very interesting. I'll come back to this concept later on, but this is a very interesting kind of charger. They call it a bi-directional charger, which means that the power can flow from the grid to the vehicle, when you want to charge it, but the power can also flow back from the vehicle to the grid if you want to make use of the stored energy, right? So this is actually very exciting development. Like previously I talked about how we want to use renewable energy sources for the power which is being used for electric vehicles. So this technology is extremely important because it is going to support photovoltaic systems, because we know that photovoltaic systems cannot produce power in the night time or in certain seasons also. So the EV batteries, which are actually very costly, these batteries will act. What I have shown here is known as a half bridge inverter. When I say that some circuit is acting like an inverter, I mean that it should convert DC to AC. So here we have DC, which I'm showing with the help of two batteries of voltage VDC and VDC. Here I have shown the load. This load requires AC to run, right? Which means that the polarity of the voltage should change periodically. So this is a challenge that we have to overcome, that this DC has to be converted to AC. Now there are a number of applications which require DC to AC conversion. One prominent application is the electric vehicle itself, but apart from that, like all the photovoltaic based power plants, they need inverters. Uh, there are UPS, it requires inverters. Many applications they require inverters. So how this conversion from DC to AC happens? Uh, it happens with the help of two switches that I have shown, marked as S1 and S2, right? So this switch is implemented with the help of semiconductor devices. A typical device that's shown here is an IGBT. So typically, like, these devices have a transistor part, which is what we call as a controllable part, right? If I'm calling it a switch, I mean to say that it can be turned on and turned off at your will. Okay, so this is a transistor part which you can control, and this is a diode which, of course, you cannot control, but the circuit will control it, right? It cannot be turned on or turned off at your will, but based on the circuit states, it will change. So this type of structure is known as a half bridge inverter. So to analyze this inverter, like, what we do is, this is the load which is connected between two terminals A and B. And this B terminal, like, I am calling it as my reference node, which means that the potential that I have assumed here is 0 volts. Now, if this is a battery of voltage VDC and this is the lower potential terminal, it is connected to this uh, terminal marked as minus here. So if 0 volt is the lower potential terminal and the battery potential difference is VDC, then higher potential terminal should be at a potential of plus VDC. Similarly, the battery which is connected at the lower side, the higher potential terminal is at 0 volts. So it means that the lower potential terminal should be at a potential of minus VDC, right? So this is the marking of the potentials that we will be using to analyze this structure. So here the working is very simple. We should remember the goal. The goal is to convert DC into AC. This load requires AC to run. So we are converting DC into AC. So when we turn on this switch S1 and we turn off the switch S2, what happens is this potential plus VDC, it appears at this terminal A. So terminal A is at a potential of VDC. Terminal B is at a potential of 0 volts. So if we find the potential difference, output voltage, which is the potential difference between terminals A and B, then it will be VDC minus 0, that is VDC. Now, if I change the combination, here what I have done is I have turned off switch S1 and the switch S2 is now on. Now, if you turn on switch S2, then what happens is this potential minus VDC, it appears at the terminal A. So now if you see, the terminal A is at potential of minus VDC. Terminal B, which we had called as the reference terminal, it is at 0 volts. So if you see the potential difference now, then it is potential at A minus potential at B, right? So potential difference will be minus VDC. So if you repeat this process, you see, for some amount of time, for example, if you want to produce an AC of 50 hertz, right? So it basically translates into a cycle of 20 milliseconds. So for 20 milliseconds, what you do is, for 10 milliseconds, S1 is on and S2 is off. And for other 10 milliseconds, S1 is off and S2 is on, right? So for the first part, like the output voltage is plus VDC when S1 is on, and when S1 is off and S2 is on, the output voltage is minus VDC. So basically, this is how you are converting DC into AC, right? For some part, the output voltage looks like this, and then this is the positive half cycle, and this is the negative half cycle, right? So you are converting DC into AC, and the core part in this conversion is being played by these switches. All right, and these switches are basically semiconductor devices. Okay, so this is what we have to remember. Whenever you're converting power from one form to another, electric power, either from AC to DC or from DC to AC, the core role is being played by semiconductor devices, which are acting like switches. Okay, so this is how we define power electronics. Now, whenever we are talking about electric vehicles, the backbone of electric vehicles is power electronics, because to drive a motor, electric motor, you need power electronics. To extract power from the battery, you need power electronics, and to deliver it to the motor, you need power electronics. To charge a battery, you need power electronics, because you have to convert AC into DC, and not just convert AC into DC, but you have to take care of the power factor also. So a lot of complicated power electronics is involved there. So that is why I am presenting this definition of power electronics here. This is actually for all streams of engineering, they can appreciate this definition. So the example that I showed here, what we were doing here, we were converting DC into AC, right? So in some other examples, some other applications, you will be converting AC into DC, for example, in charging system. So what we do in power electronics is basically we are doing conversion. So what are the possible conversions? I gave example of DC to AC. This conversion takes place inside the electric vehicle, right? To run the motor. Battery is DC and motor is AC. Another conversion which is required is from AC to DC for charging the battery, right? Another conversion which is required is from DC to DC. This is one level of DC and you are converting it to another level of DC, right? So, or from a fixed DC to a regulated DC. So DC to DC conversion. And there are many applications which require AC to AC conversion. For example, wind energy based power plants. So what we are doing in power electronics is basically we are doing these 4 types of power conversions of electric power, either from DC to AC, from AC to DC, DC to DC, or AC to AC. This is what we are doing. How we are doing it? So again, refer back to the example. We are doing it with the help of power switches, right? So these are the power semiconductor devices. They are operating in their switching mode. I'll come into it this point because this is a very important point. they are operating in their switching mode, which basically means that they're acting like either in on state or off state. No in between state is being used, right? So this is how it is being done, right? Conversion and control of electric power is being done by using semiconductor devices as switches. Now, why part is actually the mechanical engineering part? Why so much complexity? Why do we need to use semiconductor devices as switches? Because in that case only, the efficiency is high. In any power converter, efficiency requirements are extremely important because you see, there is some input power and there is some output power, and there is an amount of power which is actually wasted. This is power loss. Now, this power loss takes place through heat, and this heat has to be dissipated fast. And this heat is dissipated by using heat sinks, which are typically made of aluminum. And each heat sink adds to the weight of the converter, the size of the converter, and the reliability of the converter. Right? So it actually starts from the mechanical design, from the mechanical engineering point of view, from the point of view of heat transfer. If the efficiency is low, basically what is happening is a lot of heat is being generated by the converter. You need a huge heat sink, and it is going to affect the power density of the converter, right? So when I was talking about like the little box challenge, if you read their documents, most of them worked very hard on reducing the power losses, which basically translates into reduction in the transfer of heat. So a lot of mechanical engineering was involved there, right? Right from the design of the heat sink, the shape, the material which has to be used in the heat sink. Of course, it also translated into the type of the switches which are to be used, the controller which is to be used, and other things. But the need of power electronics actually emanates from the problem of heat transfer, right? Which adds to the weight, the size, uh, the volume, and the reliability of the power converter. Okay, so another small example, like which is again very relevant for electric vehicles. Like if you see the any e-rickshaw, you know, you have a battery and you have a load. The load is a DC motor load there. There we do not use AC motors because of to keep the costs low there. So if you want to run your motor, let us say on a voltage which is less than the battery voltage. For example, if you want to run it at 8 volts, but the battery is of 12 volts. So very simple solution is to use a resistance in between. And what will happen is that there will be a voltage drop in the resistance, and your load will see the required voltage. But the problem here is the losses in this resistance, you know, this losses will be very high. So this is not a practical solution. A very practical solution is to use a switch here. You know, this is a simpler example because only one switch is being used here. Now you see this structure, if this is in this circuit, if you turn on the switch, the output voltage instantaneous value is 12 volts. And if you see the switch is off, then this current is zero, the output voltage is 0 volts. Now the voltage required for the load was 8 volts, right? So what you do is you intelligently turn on and turn off the switches. For example, for a time of equal to capital T, you turn on the switch, the output voltage is 12 volts. And for half of the time, that is T by 2, you turn off the switch, that is the output voltage is 0. And you keep repeating it. So what happens is, if you see the average value here, which is shown with this dotted line, this average value will come out to be equal to 8 volts. Right? So you can convert a fixed voltage into a controllable DC output by an intelligent use of this switch. Now, why switch? Why only? Why are we looking for operation of a semiconductor device as a switch? Simple, because if you have a device here which has a potential difference equal to V, and the current flowing through it is I, then the instantaneous power loss is equal to Vi. Right? So if you have a switch, then it is either in the on state. On state means ideally it is acting like a short circuit, which means that the voltage difference is zero, or it is at off state, which means that the current is zero. So in the on state, if you see the power, irrespective of the current, the power loss will be zero, because V into I, V is zero here. Similarly, if you see the switch at an off state, then the current is zero. So irrespective of the potential difference across the terminals, the power will be zero. So that is actually how we achieve very high efficiency if we use semiconductor devices as switches. Right? So this is what we call as power electronics. Now this is different from another field, which is linear electronics. So I take an example of a tap. For example, I have a tap here. This is flow of water, and this is a control which you are using for the flow of water, to control the flow of water. Right? So in here you see there is no flow. We call it as an off state. Now what you can do is you can partially turn on the switch, this tap. Right? Partially on means that the water that is flowing is below the full capacity. Right? So this is partially on state 1. I can increase the amount of water that is flowing again, but this is partially on. It is not fully on. It is a state 2. I can further increase the amount of water flowing into it, but this is again a partially on state 3. And this is a fully turned on state. Where the complete volume of water is flowing, like whatever full flow is possible, a complete full flow is taking place. Right? So in our terminology, this tap is actually analogous to a semiconductor device. Now that device can be controlled, right? It can be an SCR or MOSFET or IGBT, and it can be controlled in a manner that either full current flows through it or zero current flows through it, or some kind of partial current flows through it. So if any partial amount of current is flowing, then that usage is called linear electronics. You have the same device, you can use it for partial flow of current. That technology is called linear electronics, where these devices are acting like amplifiers. Or you can use these devices either in the off state or in the on state, no linear state, which means no partial state. Right? So if you are using a semiconductor device only in switching mode, which means only in on state or off state, then this technology is known as power electronics. Right? So it is a misconception that power electronics is a combination of high power and electronics. It can be a very low amount of power, but if your semiconductor device is acting in a manner that it is either on or off, and there is no in-between state, then that technology is called power electronics. So in whole of the electric vehicle operation, either in the traction part or in the charging part, we are using semiconductor devices as switches. And I told you the reason why we are using it, because the power losses will be very low in when you're using these devices as switches as compared to their usage in their linear states, where they are acting as an amplifier. There is a significant amount of power loss which is taking place in these devices. All right, so here, like, I had a lot to discuss about, like, why further advancements are required, and for that we had to have actually small discussion on uh, the Fourier analysis, but I don't know whether it will be too much for you to take. Sridhar sir, like, can you advise, should we take up the Fourier analysis part or should we directly go into?
Sir, better to give a brief introduction in a couple of minutes and you can switch over, sir.
Okay. I'll give you a brief introduction because this is a very important part. Now, see what we were desiring. I gave you an example of an inverter, like, right, and it produced a waveform like this. This was the output that we got, but actually this is the desired output, a pure sinusoidal waveform. But you see, in principle, you cannot obtain a pure sinusoidal waveform because a pure sinusoidal waveform is a continuous waveform. It is defined at all points of times, whereas if you use a semiconductor device as a switch, then discrete transitions are bound to happen, right? So what you get is actually an alternating waveform, but it is a square waveform, which is far away from the desired output of sine wave. So how do we overcome this challenge? For this, what we use, like, a technique called Fourier analysis. So I'll briefly explain what is actually Fourier analysis and synthesis. So I have here a sine wave uh, of frequency f naught. I have taken another sine wave of frequency which is 3 times this frequency f naught. You see, this frequency is f naught, and this is a pure sine wave. This frequency is f naught, but although the frequency is more and amplitude is different, but it is a pure sine wave, right? Now, if you add these two sine waves, then what you get is a non-sinusoidal waveform, right? This waveform is not a sine wave, and it will have a frequency f naught equal to this frequency. Okay, if I add another pure sine wave of frequency 5 f naught, then the original sine wave will be actually further distorted in this to this shape. If I keep adding these, then I'll get a waveform like this, which is an approximation of the square wave that I saw. How do I obtain this approximation? By adding a number of sine waves. Now, this is a pure sine of frequency f naught. This is a pure sine of frequency 3 f naught. Again, a pure sine waveform, and again a pure sine waveform. So if we add these waveforms, then you get this non-sinusoidal waveform, and this process is called synthesis. You can synthesize a non-sinusoidal waveform by using a number of sine waveforms. You can also do the converse thing, right? You can break it down. You can break down a non-sinusoidal waveform, and you'll get a number of sinusoidal waveforms of different frequencies. This is known as analysis. This is a very powerful theorem which was proposed by Fourier. So we call it as Fourier analysis. All right. So actually, this was the desirable, if I talk about inverter, this was the desirable waveform. And all these, they should have been removed actually. Right? If we remove all of them, then we will be left with this waveform, which is actually the desirable waveform. All right. So this main waveform is known as sinusoidal waveform is known as the fundamental component, which is desirable component. All other are known as harmonics. So if the frequency is 3 times, we call it as third harmonic. If it is 5 times, we call it fifth harmonic, right? So in practical situations also, we have a feeling of this. If you have an inverter at your home, and if the power goes off, and if the load is transferred to the inverter, then you observe that the fans, they make louder noise as compared to the case when they are not running on inverters, right? Or the tube lights with chokes, they make more sound. So why those noises are coming? They are because the presence of these harmonics. So these harmonics have to be removed. This information is shown in this form. Actually, this is called a harmonic spectrum. All the softwares, they give you flexibility to produce this kind of spectrum. So these are the harmonic orders. For example, this is n equal to 1, which means that the frequency is f0. This is n equal to 3, which means that the frequency is 3 times f0. Right? This is 5 times f0, 7 times f0. So this is a comparison. If the fundamental component is 100%, then this is around 35%, this is 20%, and so on, right? So this figure is known as a harmonic spectrum. So what we want is that we want to remove these harmonics so that only this component is left, a pure sinusoidal waveform. So if we remove these harmonics, then we will get a pure sine wave, right? Which means that we have to use filters, and lower order harmonics are very difficult to remove. You have to use large amount of inductors and capacitors to remove them. Okay, so to overcome this problem, you see what we are dealing with is, we are dealing with the size of the converter, right? So if you have this kind of square waveform, then you have to use a filter which will be large in size. The lower order harmonics are difficult to remove. You have to use a large filter. The size will be more impractical for an electric vehicle. So to overcome this problem, we use a technique called pulse width modulation. This pulse width modulation, what it does is, it removes the lower order harmonics. It transfers that to higher order side, right? This is 17. This is, if you see this harmonic, this is 17th harmonic. So higher order harmonic, and the size of the filter will be reduced. All right. So if you compare this, this is a harmonic spectrum for a square wave. This is for a PWM waveform, pulse width modulation waveform. If you compare their harmonic orders, then the size of filter will be much less in a PWM waveform. Okay. So this is an important concept. The PWM technology is the heart of whole of these power converters that we are using in electric vehicles, right? So this is a similar kind of structure. This is called a full bridge structure. This structure is very popular. You see, there are 4 power switches here. This is the AC side, and this is the DC side. Now for inverter, you place the source as the DC side and load at the AC side. For rectifier, for the charging part, you place the source at the AC side, which is the grid, and the load at the DC side, which is the battery. If you see all the structures that I had shown, you see this part is a bridge part, 4 switches. This is a bridge. This is a bridge. This is a bridge, but in 3 phase. Again, the bridge. Again, the bridge in 3 phase. You see, this is a half bridge, diode-based full bridge, and half bridge, the structure that I had just discussed. A bridge in 3 phase, a bridge in single phase, again a bridge in 3 phase. So this is an extremely important part. What I was talking about is the bridge structure, right? So that is why I have taken this example. I'll come back to these slides. So now if you operate this bridge structure in a certain manner, then you have a possibility to generate 3 different voltages. If you turn on these 2 switches, the output voltage is 0 volt. This is the same analysis that I had presented before. If S1 and S4 are on, then output voltage is 2 VDC. And if S3 and S2 are on, that output is minus 2 VDC. You compare it with the half bridge structure where I had told that the output can either be plus VDC or minus VDC. Here the output is plus 2 VDC or 0 or minus 2 VDC. Right? So this is what is known as number of levels. The AC side is seeing here 2 levels, VDC and minus VDC. For this structure, the AC side is seeing 3 levels, right? So this gives the concept of a multi-level structure. If you increase the number of levels, you will actually, the imitation of a sine wave will be better. For example, this is a 3-level voltage. You see, if you compare it with a square waveform and a sine waveform, it is a very good imitation of a sine waveform, right? 3 levels. Why I'm calling it levels? 2 VDC, 0 and minus 2 VDC. So this is a 2-level waveform. This is a 3-level waveform. You see the transition. This is from plus 1 to minus 1. But here the transition is from plus 1 to 0 and 0 to minus 1. Right? So rate of change of this transition, we call it as dV by dt stress. So here you see the dV by dt stress is actually halved. So if it is an electric vehicle, the life of the motor will be more because the dV by dt stress on the load is half of it. If you increase the number of levels, you see here I have 5 levels: 0, VDC by 2, VDC, minus VDC by 2, and minus VDC. So dV by dt stress is further reduced as compared to these 2 waveforms. So this is a 2-level waveform, this is a 3-level waveform, and this is a 5-level waveform. So 5-level waveform will have much better harmonic profile. The size of filter will be less, which will save space. And this will also have much reduced dV by dt stress on the load, right? So this is an example of an advanced power converter. So the example of little box challenge that I had given you, it had a 7-level inverter, which means that the number of levels were 7. So the filter size was less, the losses were less, and that is why they were able to produce an inverter of such high power density, right? So the power circuit, the circuits which can synthesize this type of voltage, they're called as multi-level converters. Okay, so this is the main advantages is in terms of low dV by dt stress, very much improved harmonic profile, and one core electrical advantage which I'm not going to discuss is the device that you can use is will have the voltage rating will be very less. So the novel development that I was talking about, it was in association with my PhD student, is Mr. Nikant Jain, and the work was very interesting. If you remember at the beginning of the slides, the presentation, I was talking about buck rectification, how to reduce the output DC, right? So what we discussed till now was an inverter. What happens is in an inverter is you have a battery at the DC side, and at the AC side you have a load. So there number of multi-level inverters are there. They are commercialized also, and a lot of research is going on in these inverters. There's a very special class of multi-level inverters which is known as switched capacitors based multi-level inverters. What these inverters do is that if your input voltage is VDC, then the output voltage will have a peak value of 2 VDC or 3 VDC or 5 VDC, right? That is, they are operating in boost mode. We say that the voltage gain is beta. For example, beta is 2. It means that if the input voltage is VDC, then the output voltage will be AC, but the peak value will be 2 VDC. right? So this is a very new kind of development in inverters technology, the switched capacitors based boost converter. Now this research, it started with a simple question, that these structures, if they are converting DC into AC, which means that they are acting as inverter and they are increasing the voltage, is the reverse phenomenon possible? Can we do changes in these structures so that they can convert AC to DC, which is the requirement in EV charging systems, right? So, and the AC side, you will have the grid, which will act like the source, and the DC side, you will have the EV battery, which is to be charged, which will act like a load. So, can these structures, which perform the DC to AC conversion, can they act as rectifiers? And more importantly, when while acting as inverter, if they were boosting the input, then why, if performing the reverse operation, can they reduce the uh, amount of voltage? Because everything is reversed means the function should also be reversed, right? From boost, it should get translated to buck operation. So this research started with this question because uh, there is a lot of interest in achieving buck rectifiers, but not many topologies are available for buck rectification. Very upcoming area of research, right? So you can have a look at this complete research. This is a very recent paper uh, published by my team in IEEE Transactions on Power Electronics. But this question, it started with all this. So we do not have a lot of time, but I'll give you a very simple explanation of this work. So this is the conventional system, the charging system. Okay, I'm talking about G2V, where what you do is that you convert AC into DC, but it acts like a boost conversion. So if the input AC is 320 volt, the output voltage will be typically 400 volt. So you have to use a DC to DC converter and convert this 400 to 48 volt or 72 volt or 350 volt DC for charging. Okay. But in the if you use switched capacitors kind of rectifiers, then the same for the same input voltage, the output voltage will be less than the peak value. You compare here, this will be 400 and this is 120 volt. So matching 120 to the battery voltage will be very easy. Similarly, this is for the charging part, which is basically G2V. For the discharging part, if you want to achieve V2G, then also it is possible. In that case, the same topology will act like a boost inverter. All right, so both V2G, the bidirectional power flow is possible here. And you can also match the voltage, battery voltage easily with that of the rectifier system. While doing this research, we actually discovered many new things also, a very breakthrough kind of thing, which I'll show you. So I'm skipping these advantages. I'm skipping this example. This is the circuit that we had designed. You know, it is a switched capacitor circuit, so it has multiple capacitors here. The target is to convert this AC to DC here, and to a buck DC actually. All right. So while doing this, we were able to achieve this target. You know, we were for an input of 325 volts. We were able to obtain an output of, you see, from this 325 to 70. You know, in the beginning, I talked about wide range of voltage. So we were able to achieve a wide range of voltage based on the kind of car that you're having. You can decide an operating point and you can obtain that voltage at the rectifier. But like some of you may also ask that what happens if the voltage is more? So very interestingly, the same topology was acting as a boost rectifier also. The amount of voltage was, output voltage was more than the peak value of the input. Right? Of course, the number of levels change. I talked about multi-level also. Like this is the best part, best range, where it is acting in 7 levels, which means that filter requirements are very less, and it is acting in buck mode. You can also operate it in a 5-level mode. It will operate in, again, buck mode. But if you shift to 3 levels, then it will act in boost mode. It means that the same rectifier can operate in buck mode as well as boost mode. Although we had started with the presumption of buck mode. So we did a number of experimentations on it. So we were able to achieve, very importantly, we were able to achieve a unity power factor operation. This is the grid voltage and this is the grid current. So you see that the grid current is almost sinusoidal and it is in phase with the voltage. The voltage at the rectifier side, it was a 7-level voltage, which means that the harmonic profile was very good. The output voltage, you see, it is less than the peak of the input voltage. So we were able to get a buck rectification mode. This is a 5-level mode. Again, the voltage is little increased. This is the 3-level mode. And you see it is acting like a boost rectifier here. The output voltage is more than the peak of the input. And again, this is a buck operation, but over modulation. Here, what we saw is that the grid current, the distortion is too much. So this is an undesirable mode. We tried this whole converter with a lithium-ion battery, and the kind of performance that we were expecting, we achieved that kind of performance both in stationary, in the steady state, and in transient conditions. But very interestingly, in terms of applications, like you can use these converters both for onboard and offboard chargers. Right? For example, this is for an onboard charger. DC to DC converter here is the conventional buck boost converter. So what we would achieve is a V2G performance, right? So the flow of power was possible from both grid to battery and battery to grid. We could also extend this to its 3-phase version to make a 3-phase fast charging station with it. And for that also, like the experimental results were they were up to the mark. All right. So to conclude, like buck rectification is extremely suitable for EV charging technology. Most of the charging stations that you see, they use boost rectification, which means that the passive component requirements for them is very high. So buck rectification will be more suitable for these applications of EV charging, especially like if you are using a switched capacitor based technology. The bidirectional power flow is possible, which means that you can operate it in V2G mode or V2H mode or V2V mode, right? And very interestingly, unexpected but very good result is that it can work both in buck mode and boost mode also. Right, so this is all I wanted to share. If you have any questions, please let me know.
Thank you very much.
Thank you so much, sir. Sir, how the participants, are they going to answer? Are they
Yes, sir.
going to
Yes, sir. Yes,
ask
sir.
the
We
questions?
received some queries. Thank you very much, Dr. Krishna Kumar Gupta, sir, for your lecture on the today's section, particularly on power converters used in EV charging, converters for EV charging, and rectifiers in charging, and manufacturing aspects of battery. Particularly, you quoted the examples of Hyundai, Renault. That explanation become fruitful for us to enlighten our knowledge related to the manufacturing aspects of battery. And next, your explanation related to converters for EV charging is very useful for the participants. and you integrated mechanical engineering aspects in improvement in development of charging systems. That is a very nice presentation, sir. We are very happy to hear that aspect. And some of the participants, they told that you have enlightened the basic concept of the power electronics. Even some of us, including myself, doesn't know about that concept. With your explanation, we got that basic idea about the power electronics. Thank you very much, sir. And some of the participants, they have posted their questions. I'm going to present them.
I think
Mr.
some of you are asking
sir.
about wide band gap devices.
Yes, sir. Yes, sir.
See, wide band gap devices, especially gallium nitride and silicon carbide, they have been commercialized very recently. With these devices, we can achieve very high frequency of operation. Like I was talking about PWM, pulse width modulation. So with wide band gap, this is a very good question. I congratulate the person who is asking this question because this is a very good observation. I was talking about the little box challenge. Most of the participants, they had used wide band gap devices because the switching frequency there can be as high as 10 megahertz. That is a very huge switching frequency, which basically translates into reduced size of electromagnetic components, right? So wide band gap devices, the switching losses in high frequencies is very low, and that is why we are using wide band gap devices, although as of now they are a bit expensive. But my guess is that, like, in time to come, like, all of the converters will be using wide band gap devices. So commercially, like, you can use silicon carbide based devices or gallium nitride based devices. They are coming up with very new materials also, but they are not yet commercialized.
Thank you, sir. Dr. Singh is asking to share the name of a good book to start with the design and fabrication of the power converters.
Sir, what I'll
Related
do
to
is
design.
I'll share those links with you. Okay, I have a
Okay,
collection
sir.
of books which talk about practical aspects of power converter design. So I'll use those books. I'll share those links with you, and then you can share it with the participants.
Thank you, sir.
Will that be all right?
Yes, sir. Yes, sir.
Okay, sir.
One question that you believe that future will be electrical vehicle. It is true mean that what about GDP of Gulf countries?
See, electric vehicles, they are facing a lot of resistance actually. Apart from the technical reasons, there is a lot of political reasons also. Gulf countries, they have a lot of say on the global prices of oil, right? So actually, the instability in global prices is one of the important reasons why many countries are going for electrification of this vehicular technology. If the prices were stable and the countries, like, they could have reliable sources of uh, this gasoline and all, then they must not have pushed electric vehicle too much. But this is one of the reasons actually. Of course, everybody should be worried about the GDP of the Gulf countries, but this instability in the global prices, wars are the wars, they change everything, because of our dependence on fossil fuels. So what I feel is that, probably I have quoted the right words there. You cannot stop an idea whose time has come. Many factors are fueling this electric vehicle revolution. One of them is, the global prices of oil. So probably the Gulf countries, they have to find uh, other ways. But another thing is that, many countries, they burn oil too for production of electricity, especially in Europe. So probably that oil, it will go into production of electricity. But I'm not
Thank
the
you,
right
sir.
person to answer this. I cannot.
Thank you, sir. Next is from Miss Divyashree. Madam is asking a question. Suggest simulation software for EVs.
If you want to have a complete simulation of the machine and the power electronics, then Maxwell is the software.
Maxwell.
Maxwell, there you can take care of the complete mechanical part, the thermal part, the power electronics part, and the machines part. Industrially, it is very popular. In industries, they use it very much. If you're interested only for the power conversion part, then uh, uh, Plexim is a company which makes a software called Plex, Plecs. That software is good because there you can do a heat sink design. Thermal flow can be modeled there. So without that modeling, like, there is no point of designing a power converter. In MATLAB Simulink, you can get an idea of the working of your converter, but the actual design, you have to take help from this software called Plex.
Next
So I
question is
recommend two
from
softwares, Plex
sir.
and Maxwell. Maxwell is a bit complicated because it involves, because you can interface it with the machine design part also, but it is very powerful. Electromagnetic design can be done in addition to power electronics, power converter design.
Thank you, sir. Next is from Ms. Indupriya, madam. Which type of converters are more suitable for lithium-ion batteries?
The battery, if you're talking about battery life, then at the back end you have to use a DC to DC converter, right? I talked about charging stations in two stages. First stage is the AC to DC conversion, where you are maintaining the power factor. The second stage is a DC to DC converter. So for lithium ion batteries, like most of the manufacturers, they are using a topology called dual active bridge, DAB. They call it DAB. So DAB has soft switching features, and you can impose a strict control of current that is being injected into lithium ion battery. So the most popular topology for this charging, see, AC to DC conversion part does not have much role to play. DC to DC conversion part has a role because it is going to inject current. So DAB is a very popular topology, dual active bridge, the best one for it as of now.
Thank you, sir. Next is by Ms. Sharmita, madam. The question is, what type of switches are preferable for IGBT, MOS, FET, GTO, or any other advanced switches? Please kindly share it if possible.
See, for electric vehicle traction systems, if madam is from electrical engineering, then you see, if it is for a traction system, then most of the manufacturers, they are using either permanent magnet synchronous motor or three-phase induction motor. And for both of these motors, like the speed control is basically, it is based on the control of the frequency, output frequency. Okay, which basically means that the switching frequency has to be of wide range. For example, if the output frequency is 400 hertz, then the switching frequency cannot be limited to 1000 hertz. It has to be much more than that. So for traction applications, MOSFET is the most appropriate candidate because the switching frequency that you can achieve there is very high. For the charging system part, because the voltage levels are high, IGBT is most appropriate. I have not yet seen any commercialized system which uses GTO. So probably GTO are not in much of favor from the manufacturers. For charging systems, IGBTs, and for traction drives, MOSFETs are being used. That
Thank you,
is
sir.
what is my understanding.
Thank you, sir. Next one is by Mr. S.C. Murthy.
Sir,
Sir, why use wide band gap semiconductor in converters?
because like if uh, in converters, if you can increase the switching frequency, then the size of inductors and capacitors in that converter will be highly reduced. That is why people are using wide band gap. Larger is the frequency, smaller will be the size of passive components. That is why wide band gap devices are being used.
Thank you very much, sir, for your patience answering the questions. We got good information from your section. Sir, if you can stay, we will start the valedictory section immediately.
Yeah,
Please be
sure.
on line, sir. Immediately we are starting.
Sure, sir, sure.
Well, the time has come to the curtain to our program as we come to the close of it. A very good afternoon and a warm welcome to everyone to this voluntary program on the one-week online faculty development program on trends and challenges in the development of electric and hybrid electric vehicles. During the past few days, we have had several insights on to various topics of electric and hybrid electric vehicles, its development, challenges, and also probable remedies for the same. We had eminent personalities from different fields who have enlightened us, both on the national and international levels. I hope all of you had a wonderful time during these sessions and have learned much from the resource persons. This afternoon, I would like to acknowledge the dignitaries present with us. Our Head of Mechanical Engineering Department, Dr. Satish Pujari. Our Chief Guest Speaker for today, Dr. K.K. Gupta sir from Thapar Institute of Engineering and Technology, Patiala, and our convener for the event, Dr. K. Sridhar sir. Firstly, I would like to invite our convener for the event, Dr. K. Sridhar sir, to give a brief report on the FDP. Over to you, sir.
Good noon to all the dignitaries. Dr. Krishna Kumar Gupta sir, today's guest speaker for our validity section. Dear participants, most of the automobile companies are going to switch over to electric, a cleaner and sustainable alternative. Electrical vehicles are not just the wave of the future, they are saving the environment. EVs have smaller carbon footprints than gasoline powered cars, no matter where your electricity comes from. We are hearing about challenges in development of EVs. Even young generation also getting many questions in their mind related to battery life, why it is less, frequent recharging of battery, recharging time is high. What about charging systems, charging stations, swapping stations, battery recycling system? With these aspects, we plan to conduct one program on trends and challenges in development of electric vehicles and hybrid electric vehicles. The objective of this FDP is to introduce fundamental concepts, principles, analysis, and design of electric and hybrid electric vehicles. The program focused on global scenario in development of electric and hybrid electric vehicles and electric vehicle developments, multifunctional charging systems, energy management strategies, research aspects, and troubleshooting. In this aspect, we invited the speakers to address the participants. Very limited people are available across the globe who are carrying out that research, including our guest today's validity section, Dr. Krishna Kumar Gupta sir. With the acceptance of speakers, we invited the participants. We have shared the brochure to all the possible participants, and we have received good response across the globe. And the participants from abroad also, they have shown interest. participants from Algeria, Bangladesh, Ethiopia, Germany, Malaysia, Nigeria, Pakistan, Philippines, Saudi Arabia, Singapore, Sri Lanka, Taiwan. And from USA, we got the responses from Colombia, Michigan, New York, Pennsylvania, North Carolina, and South Carolina. And from our India, registrations are from all the states, including Northeast states and Union territories. Then we planned the program in 5 sections. First day, inauguration address is planned. Dr. Satish Pujari sir, HOD and convener of the program, Learning Institute of Engineering and Technology, has given inaugural speech. Then Mr. Avinash Kishore sir, General Manager R&D, Revolt Motors, Gurgaon. His address is on trends and challenges in electrical vehicle design. Sir has good exposure related to the research and developmental activities of EVs. And particularly for bikes, he has given many case studies and what is the real problems they are facing and problems they are receiving at the service stations, how they are rectifying the problems and what more challenges are there still to improve the design. He has given a wonderful speech. Second day by Dr. Shailendra Kumar Dwivedi sir from NIT Bhopal. He addressed the participants related to integration of multi-spot EV-based charging infrastructure. Third day, Mr. Rohit T, Project Manager, Automotive EMEA, TE Connectivity from Germany. He has explained the global scenario, what about the situation in different automobile companies across the globe. He explained and discussed the issues related to the development of electric vehicles and hybrid electric vehicles. And he answered many queries posed by the young generation. And he integrated the concepts of mechanical engineering discipline and electrical engineering discipline. And what are the future aspects in research and development of the electric vehicles. He explained very nicely. Then fourth day, Dr. Lalit Kumar Sahu sir from NIT Raipur. He explained the recent trends and advancements in EV and charging stations. We got good information from Dr. Lalit Kumar Sahu sir. And in today's section, Dr. Krishna Kumar Gupta sir from Thapar Institute of Engineering and Technology. He explained advanced power converters for electrical vehicle charging. And speakers, they quoted many examples related to the troubleshooting at present and how the rectification is going on, what research is going on. And persons from industries, they explained business opportunities related to EVs, EV leasing, establishing EV fleet, public charging stations, swapping stations, battery recycling business, grid energy storage modules, EV service and maintenance, battery pack and cell manufacturing, solar integrated with EV charging, EV training services. They explained nicely. Now today we have Dr. Krishna Kumar Gupta sir with us from Thapar Institute of Engineering and Technology. Then Professor Daniel sir will take up the further proceedings.
Thank you very much, sir. Thank you for enlightening us on what happened over the past week. Well, now it's time to hear from the participants. I would like to invite the participants to share their views on the FDP and give us feedback so that it will enable us to meet your needs in an even better way for the next FDP or the follow-up workshops. And when I say feedback, it doesn't mean only the good ones. You might as well share point out the bad ones so that there might be hiccups here and there. So you're most welcome to share anything. So if anybody would like to share, please use the hand raise option so that we can unmute you. If anybody would like to share, please raise your hand raise option. Yes, we have Mr. Savant Anurag Ramakrishna. We have Nandji. Sir, can you please share?
Am I audible, sir? Am I audible?
Yes, sir, you're audible.
Yes, sir. Yes, sir. Audible, sir. Please continue.
Okay, sir. Just I want to ask something on hybrid and electric vehicle. First of all, just I want to introduce myself, sir. I am Nandji, and I am teaching in JSPM Engineering College as an assistant professor. And I have started working on hybrid and electric vehicle in month of January this year. So I have gone through various research papers as well as concepts which have been implemented in industries as well. Meanwhile, while doing something in hybrid and electric vehicle, we have always faced problems in modeling these vehicles. Say, for example, most of us are teaching in private colleges where machineries are not available. However, companies have sponsored a laboratory, but in that laboratory, they have only kept models. But we want those results which are very specific to industries. Say, for example, if some of us are working in battery management systems, so they would like to plot those graphs which are quite useful in research works. Say, for example, that state of charge and discharge, so on and so forth. So how to do these modeling activities, sir? Say, for example, MATLAB is one of that software where we can do modeling. And if we are modeling these things, what should be our approach? Means how we should start with that. Say, for example, we should have some model. If that model is available, then we can think for its parametric inputs. And if inputs will be given to that model, say, for example, that model is formula, or if it is a 1D or 2D or 3D models, if available in some textbooks or research papers, I don't know. Experts may know about this. So if these models are available, we can feed some inputs, and based on that, it is going to plot some graphs based on that battery management system. So, as a conclusion, I just want to summarize my question. I just want to ask about modeling. How to do modeling of these hybrid and electric vehicles, and what are the challenges and opportunities available in these areas, and which software is to be utilized for us who are beginners. Over to experts.
So the queries can be taken later on after the validity. This is only for the feedback is only for your opinions on the FDP. Please kindly limit to that. Thank you very much. Anybody else would like to share on the FDP? Yes, we have Mr. Murugan.
Inputs on battery management systems and all, and whichever things going on in industries nowadays. So all systems are very nice, sir. That's been my feedback.
Sir.
Yes, sir.
Hello,
please go ahead.
Muruganandam from Fourier College of Technology, Coimbatore. Session was very nice and informative. And as per the request of everybody, at end of the session, you please share the PPT's videos and as well the details about the speakers. There were big peoples, and it will be useful for us for further context. Thank you.
Sir,
Sure,
already we informed all the participants. At the end of the validatory section, we'll share all the PPTs and videos also. All will be shared to the participants. Already we
Sir, the
informed
details about the
all
speakers,
details.
sir.
Definitely will share, sir.
Thank you, sir. Thank you very much.
Thank you, sir. We have Mr. Savant. Sir, you can unmute yourself and talk.
Thanks. Hello. Am I audible?
Yes, sir, please go ahead, sir.
Sir, thanks for organizing such a wonderful FDP. For 1 week, this journey was quite great upgrading for me. A lot of things I have learned, and those things were somehow just remain backwards. Means those who are not were get upgraded to the next level. So in this FDP, I get much more knowledge. And thanks for organization such a great FDP through which where means each and every day there were new resource person. They explain their journeys and their experience about the electric vehicle, and this whole on knowledge process was great. And thanks, I let the last. Thanks, sir.
Thank you, sir. Thank you very much. Okay, I don't think we have anybody else, so we'll move forward with the program. Right. So before we hear from the head of the department, I request all the participants, if you can turn on your videos, we would like to take a snapshot of the gathering. If you can turn on your videos for one minute. Yes, thank you very much. We would like to take a snapshot. If you can just hold on for 1 minute. Thank you. If you can hold on for a few more seconds. Thank you very much, participants, for your cooperation. To formally end this validity section of this program, I request our head of the department, Dr. Satish Pujari, sir, to render the vote of thanks, after which we will close this 1-week online faculty development program on trends and challenges in the development of electric and hybrid electric vehicles with a few announcements and the national anthem.
Thank you, Daniel. Dear faculty, friends, delegates, distinguished guests, committee members, greeting from the Department of Mechanical Engineering, Lindy Institute of Engineering and Technology. On behalf of the organizing committee, I would like to express my appreciations and thanks to all the participants of this 1-week FDP on trends and challenges in the development of electric and hybrid electric vehicles, which was held during 26th to 30th September 2022. It has been our pleasure to host all the participants of the FDP via the online platform. The participants were very enthusiastic. I'm thankful to all the participants for joining from different parts of the country and also from the abroad. We have been fortunate to have some of the eminent persons from the academia working in the area of electric and hybrid electric vehicles. I'm sure that the participants must have benefited by attending this FDP. I'm very much thankful to the management for funding this FDP. Without their generous financial support, it would not have been possible to organize this event. My sincere thanks to Honorable Chairman Sri Madhusudan Rao Garu, Honorable Vice Chairman Sri Srinivas Rao Garu, Honorable Secretary Sri K. Sivaram Krishna Garu,
for their constant encouragement throughout this event. I am very much thankful to the principal, Dr. V.V. Ramareddy Garu, for continuous support and advice, which was greatly helped towards the successful organization of this FDP. I sincerely thank our chief guest and keynote speaker for the first day, Dr. Ritesh Keshri from NIT Raipur, for kindly accepting our invitation and gracing the inaugural function. A very special thanks for all the speakers who spared their valuable time and graced this faculty development program. I also thank Dr. Krishna Kumar Gupta, chief guest and speaker for today's session from Thapar Institute of Engineering and Technology, Patiala, for sharing his valuable thoughts. Special thanks to all the other resource persons, namely. I am also thankful for organizing this organizing team at Lending Institute of Engineering and Technology. I acknowledge the unwavering support received from the faculty and staff members. My thanks also go to all the people who have given their precious time to make this event memorable. The convener for the event, Dr. Sridhar, the organizing team led by the coordinator, Mr. Daniel Silas Kumar, along with Mr. Gangadhar, Mr. Jagadish, Mr. Kamesh, Mr. Ravi, and others. I finally would like to thank all the participants who have given their valuable feedback. We will definitely take your feedback and improve for the next one. The response for this update is tremendous, and we are sure that we would be organizing series 2 on the same topic very soon. This time in an even better way, by taking into considerations and feedbacks of the faculty as well as the keynote speakers. I once again thank everyone whose contributions has made this FDP a successful one. Thank you very much.
Thank you very much, Dr. Satish Pujari, sir. Now I am requesting our guest for this validity section, Dr. Krishna Kumar Gupta, sir, to speak a few words on this occasion to express his views and suggestions related to the program, because we are planning to continue the program in series 2 and series 3 also. We are inviting, sir.
Yeah, sir, thank you very much. First of all, I'm very much thankful to you for giving me this opportunity. And right from the beginning, like what intrigued me most is that the mechanical department of your institute is going to conduct this program. So it was a very nice on your part, because we have to break this barrier. Actually, the mechanical engineers, they should not feel threatened by the evolution of electric vehicles, and the electrical engineers, they should always consider that mechanical engineering actually forms the core of all the technologies which are being used in electric vehicles. So my sincere congratulations to you all for actually breaking this barrier. I have never been invited by like mechanical people from any institute to speak on these topics. So my sincere congratulations to you all. And I see a lot of enthusiasm in the participants, and my congratulations to all of them. And they know all the experts who are speaking, and they should feel free to contact them for any kind of queries. And there were actually many interesting questions also, which indicates that the participants have been very deeply involved in whole of this program. So my congratulations to both of you, like the organizers and the participants. Like you have been for the past many days, like there has been a strong bond of learning and sharing things. So thank you again, thank you very much, and thank you for the pains, Professor Sridhar. Like, and I apologize for today's delay. Somehow things were not working, so I had to borrow a laptop from one of the students. Nothing was working here, so I'm sorry for the delay that I had caused in the morning. Thank you very much.
Thank you very much, sir. It's been an honor to have you for this FDP. Dear participants, before we close, I would like to inform that the feedback come online assessment test will be posted in the WebEx chat box. It will be open till 1 p.m. only. So the participants who have fulfilled the criteria of attendance and the marks in the online assessment test will receive the certificates along with the recorded lectures. The certificates can be expected within 7 to 10 days, keeping in mind the Dashra vacation in between. So please kindly cooperate with us, and thank you very much. Shall we all, as the national anthem is being played now, shall we all rise up?
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड़ उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
Jai Hind. With this, we have come to the end of the FDP. I hope you have learned something new during this past few days. That's all from my side. The link has been posted in the chat box right now. The feedback from online assessment test link has been posted in the chat box right now. So have a great day. Until next time, Daniel signing off. Thank you very much.